following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, now where am I with this problem? Well, last time I spoke about what the situation's like as alpha goes to infinity. And I want to say also a word about, more than a word, about alpha going to 0. And then the real problems come when alpha is in between. The real problem, the situations, these ill-posed problems that come from inverse problems, trying to find out what's inside your brain by taking measurements on the at the skull, all sorts of applications involve a finite alpha, and I'm not quite ready to discuss those topics. I mean, roughly speaking, and I'll write down a reminder now. What happened when alpha went to infinity? When alpha went to infinity, it enforced this part became the important part. So as alpha went to infinity, the limit was u infinity, as I call it, u infinity. So u infinity was a minimizer of this one. U infinity minimized bu minus d squared. And in fact, in my last lecture, I was taking bu equal d as an equation that had exact solutions and saying how did we actually solve bu equal d. So u infinity minimizes bu minus d, but that might leave some freedom. If b doesn't have that many rows, if its rank is not that big, then this doesn't finish the job. So among these, if there are many, and that's what we're interested in, u hat infinity, that limit, will minimize the other bit, au minus b squared. Does that make sense somehow? This is in the problem here for any finite alpha. As alpha gets bigger and bigger, we push harder and harder on this one. So we get a one that's a winner for this one, but the trace of this first part is still around. And if there are many winners, then having this first part in there will give us among the winners, the one that does the best on that term. And small alpha going to 0 will just be the opposite, right? This finally struck me over the weekend. You know, like I could divide this quantity, this whole expression by alpha, so then I have a 1 there, and a 1 over alpha here, and now as alpha goes to 0, this is the big term. So now shall I call this u0 for brilliant notation, right? This produces a u alpha. In that limit, it converges to a u infinity that focuses first on this problem. But in the other limit, when alpha is going to 0, it's this term that's biggest. So u0 minimizes au minus b squared. And if there are many minimizers among these, well, you know what I'm going to write. u0, or I see I put a little hat there. Did I don't know, I haven't stayed with these hats very much, but maybe I'll add them. U hat minimizes the term that's not so important, bu minus d squared. Okay. So today's lecture is still about these limiting cases. as I said, the scientific problems, ill-posed problems, especially these inverse problems, give situations in which these limiting problems are really bad. And you don't get to the limit. You don't want to. The whole point is to have a finite alpha. But choosing that alpha correctly is the art. Let me just say, why? So I'm sort of anticipating what I'm not ready to do properly. So I'll say, why a finite alpha? On Wednesday. Why? Because noisy data. Even because of the noise, at best, U is only determined because of the noise up to some order, say order of some small quantity delta that measures the noise. This is like a measure of the noise. Then there's no reason to do what we did last time, like forcing BU equal D. There's no point in forcing BU equal D if that equation, if the D in that equation has noise in it, then pushing it all the way to the limit is unreasonable and may produce a very, a catastrophic illness. So that's when, so it's really the presence of noise, the presence of uncertainty in the first place that says, okay, a finite alpha is fine. You're not looking for perfection. What you're looking for is some stability, some control on the stability. Okay, right. But now, so that's Wednesday. Today, let me go, I didn't give an example. So today, two topics. One is an example with BU equal D. That was last lectures, and that's the case when alpha goes to infinity. And then secondly is something called the pseudo-inverse. You may have seen that expression, the pseudo-inverse of A. And sometimes it's written A with a dagger or A with a plus sign. And that is worth knowing about. So this is a topic in linear algebra. It would be in my linear algebra book, but it's a topic that never gets into the 1806 course because it's sort of a little late. And that will appear as alpha goes to 0. Right. So that's what today is about. It's linear algebra because I'm not ready for the noise yet. But it's the noisy data that we have in reality, and that's why in reality alpha will be chosen finite. Okay, so part one then is to do a very simple example with BU equal D. And here's the example. Okay, so this is my sum of squares in which I plan to let alpha go to infinity. So A is the identity matrix and B is 0. So that quantity is simple. Here I have just one equation. So P is 1. P by n is 1 by 2. I have just one equation, U1 minus U2 equals 6. And in the limit as alpha goes to infinity, I expect to see that that equation is enforced. And so there's two ways to do it. We can let alpha go to infinity and look at u alpha going toward u infinity, maybe with their little hats, or the second method, which is the null space method, which is what I spoke about last time. The null space method solves the constraint bu equal d, which is just u1 minus u2 equals 6. Okay, and that's, maybe I'll start with that one, which looks so simple, of course, just to solve u1 minus u2 equals 6. I mean, everybody would say, okay, solve it for u2 equals u1 minus 6. So here's the method any sensible person would use, but this course doesn't. Okay, the sensible method would be u2 is u1 minus 6. Plug that into the squares and minimize. So when I plug this in, of course, this is exact. And this becomes so I'm minimizing u1 squared plus, what was it, u1 minus 6 squared. So that's reduced the problem to one unknown. This is the null space method. The null space method is solve the equation and remove unknowns. Remove p unknowns coming from the p constraints, and here there's p is 1. Okay, and by the way, can we just guess, or not guess, but pretty well be sure, what's the minimizer here? Anybody just tell me what u1 would minimize that? Just make a guess, maybe. I'm looking for a number sort of halfway between 0 and 6 somehow. I mean, you won't be surprised that the u1 is 3. And then from this equation, I should learn that u2 is minus 3. u2 infinity, now I've got too many, u2 infinity is minus 3. Anyway, simple calculus, if you just set the derivative to 0, you'll get 3, and then you get minus 3 for u2. So that's the null space method, except I didn't follow my complicated QR orthogonalization, and I just want to do that quickly to reach the same answer. And to say, why don't I just do this anyway? This would be the this would be the standard method in the first month of linear algebra, would be to use the row reduced echelon form, which of course is going to be really, really simple for this matrix. In fact, that's already in row reduced echelon form. Okay, elimination as row reduction has nothing to do to improve that. And then solve, and then plug in and go with it. Okay. Well, the thing is that row reduced echelon form, the stuff you teach, is not for large systems guaranteed stable. It's not numerically stable, and the option of orthogonalizing is the right one to know for a large system. So you'll have to allow me on this really small example to use a method that I described last time, and I just want to recap with an example on the small system. Okay, so what was that method? So this is the null space method using QR now. The MATLAB command QR. So what did we, QR of B prime. Do you remember that we took that's the MATLAB command that eventually will, or is actually already in the notes for this section, and those notes will get updated. But that's step 1 in the null space method, QR of B prime. And this gives me a chance to say what's up with this QR algorithm. I mean, after LU, QR is the most important algorithm in MATLAB. And so what does it do? B prime, the transpose of B, is just 1 minus 1, right? Okay. Now, what does Gram-Schmidt do to that matrix? Well, the idea of Gram-Schmidt is to produce orthonormal columns. So the most basic Gram-Schmidt idea would say, so what would Gram and Schmidt say? They'd say, well, we only have one column, and all we have to do is normalize it. So so Gram-Schmidt would produce the normalized thing times square root of 2. That would be the Q, and this would be the R, 1 by 1, in Gram-Schmidt. Okay. But here's the point. That the QR algorithm in MATLAB, which no longer uses the Gram-Schmidt idea, instead uses a householder idea. And one nice thing about this is that it produces not just this column, but another one. It produces a column for it completes the basis to a full orthonormal basis. So it finds a second vector. So ordinary Gram-Schmidt just had one column times one number. What QR actually does is ends up with two columns. And well, everybody can see what's the other column in that has length 1, of course, and is orthogonal to the first column. And now that is multiplied by 0. So this is what QR does. We have this 2 by 1 matrix. It produces a 2 by 2 times a 2 by 1. And you may say it was wasting its time because to find this part, because it's multiplied by 0. But what are we learning from this vector? From this 1, 1 vector, or 1 over square root of 2, 1 over square root of 2 vector? What good can that do us? It's the null space of B. So B was 1 minus 1. So that's the connection with the null space of B. If I look at vectors, if there's my matrix B, and if I'm solving BU equal D, see, if I'm solving BU equal D, then U is U particular and U null space. And if I want U null space, then that's where this, and these, whatever extra columns, this might be P columns, and then this would be N minus P columns. That's what that's good for. And of course, that column tells me about the null space, which for this matrix is one-dimensional and easy to find. Okay. So that maybe just so you know the difference between Gram-Schmidt's QR, which stops with, if you had one column, you end with one column, and the MATLAB householder QR, which finds a full square matrix. Okay, just good to know, and here we found a use for it. Okay, so then the algorithm that I gave last time, and I'll give the code in the notes, goes through the steps of finding a U particular. And actually, the U particular that it would find, happens to be 3 minus 3, happens to be the actual winner. And therefore, the U null space that algorithm would find, if I went through all the steps, you would see that because I'm in this special case of B being 0 and so on, that the vector that it would choose, this is the basis for the null space, but it would choose 0 of that basis vector and would come up with that answer. Okay, so that's what the algorithm from last time would have done to this problem. I also, over the weekend, thought, okay, if it's all true, I should be able to use my first method, the large alpha method, and just find the answer to the original problem and let alpha go to infinity. Are you willing to do that? That might take a little more calculation, but let me try that. I'm hoping, it approaches this answer. This is the answer I'm looking for. Okay. So do you mind just, suppose I had to do that minimization. Again, now I'm not using the null space method, so I'm not reducing. I'm not getting U2 out of the problem. I'm doing the minimum as it stands. And so what do I get? Well, I've got two variables, U1 and U2. So I take the derivatives with respect to U1. I'm minimizing. Everybody, when I point, I'm pointing at that top line. So it's 2U1. And what do I have here? 2 alpha U1 minus U2 minus 6. Is that the equaling 0? Did I take the U1 derivative correctly? Now if I take the U2 derivative, I get 2 U2s. And now the chain rule is going to give me a minus sign, so it'll be a minus 2 alpha U1 minus U2 minus 6 equals 0. So those two equations will determine U1 and U2 for a finite alpha. And then I'll let alpha head to infinity and see what happens. Okay, first I'll multiply by a half and get rid of those useless 2's. And then solve this equation. Okay, so what do I have here? I've got a matrix. U1 is multiplying 1 plus alpha. U2 has a minus alpha. In this line, U1 has a minus alpha. U2 has a 1 minus minus plus alpha. Am I right? Times U1, U2 equals, what's my right-hand side? I guess the right-hand side has alphas in it. 6 alpha and minus 6 alpha, I think. Okay. Okay, two equations, two unknowns. These are the normal equations for this problem, written out explicitly, and probably I can find the solution and let alpha go to infinity. You're going to say, what are you doing, Professor Strang, this elementary calculation? But there's something sort of satisfying about seeing a small example actually work, at least to me. Okay, so how do I solve those equations? Well, good question. With a 2 by 2 matrix, can I do the unforgivable and actually find its inverse? I mean, it's like not allowed in true linear algebra to find the inverse, but maybe we could do it here. So U1, U2 is going to be the inverse matrix, which is, so my little recipe for finding inverses is take the entries, this entry is up here. That entry goes down there. Well, couldn't see the difference. This entry stays the same, but stays in place. Those change sign. And then I have to divide by the determinant. So what was the determinant of this? 1 plus 2 alpha plus alpha squared minus alpha squared. I get 1 plus 2 alpha. And that's the inverse matrix now that's multiplying 6 alpha and minus 6 alpha. Okay. And if I can do that multiplication, I have, well, there's this factor 1 over 1 plus 2 alpha. And what do I have? 6 alpha squared minus 6 alpha squared, I think 6 alpha. 6 alpha squared minus 6 alpha squared plus minus 6 alpha, I think it's that, minus 6 alpha. And, ready for the great moment, let alpha go to infinity. And what do I get? As alpha goes to infinity, the 1 becomes insignificant. The alpha cancels the alpha, so that approaches 3 minus 3. Okay. So there you see the large alpha method in practice. Okay. And you see what, well, there's something quite important here. Something quite important, and it's connected with the pseudo-inverse. The pseudo-inverse, so now I want to, we got this answer. And what I want to say is that the alpha, the limiting alpha system has produced the pseudo-inverse. So now I have to tell you about the pseudo-inverse and what it means. And basically, the essential thing that it means is the pseudo-inverse gives the solution, U, which has no null space component. That's what the pseudo-inverse is about. And I'll draw a picture to say what I'm saying. But it's this fact means that this part, which was this number, is the output. This is the pseudo-inverse of B applied to 6, 6. You see the point. B hasn't got an inverse. B is 1 minus 1. It's a rectangular matrix. And it's not invertible in the normal sense. I can't find a two-sided inverse, a B inverse. Doesn't exist. But a pseudo-inverse counts. So just to give the MATLAB, as long as I've written a MATLAB command here, why don't I write the other MATLAB command? U is the pseudo-inverse. You remember that pseudo starts with the letter P, so PINV of B multiplying D. That's what we got automatically. And it's what we get, and the reason we got the pseudo-inverse. So let me just say what was special here. What was special that produced this pseudo-inverse that I'm going to speak about more was this choice A equal the identity and B equals 0. The fact that we just put the norm of U squared there. So this, the idea is this produces the pseudo-inverse. And if you like, yeah, so can I say a little more about the pseudo-inverse before drawing the picture that shows what it's about? So I took this thing and let alpha go to infinity. Okay. So I could equally well have divided it by alpha. If I divide the whole thing by alpha, that won't change the minimizer, certainly. The same u's will win. And now I see 1 over alpha going to 0. And that's where the pseudo-inverse is usually seen. We take the given problem, which does not completely determine U1 and U2, and we throw in a small amount of norm U squared, and find the minimum for that. Right. So, yeah. Let me say it somehow. I take the B transpose B plus the 1 over alpha I. Now 1 over alpha is still going to infinity in this lecture. So 1 over alpha, this is the whole thing is headed for 0 times the norm of u squared. This is the u1 squared plus u2 squared. Okay. And that inverse, that quantity inverse approaches the, well, once I'm not giving the complete formula, but this is what's entering here, and it produces, leads to, so may I say the vague word, leads toward the pseudo-inverse B plus. Yeah, and I'll do better with that. Okay. I want to go on to the picture. Okay, so, right. Do you know the most important picture of linear algebra, the whole picture of what a matrix is actually doing? Here we have a great example to draw that picture. So here's the picture that 1806 that's at the center of 1806 for our 2-by-1 matrix. So this is our matrix is B equals 1 minus 1. This is the picture for that matrix. Okay, so that matrix has a row space. The row space is the set of all vectors that are combinations of the rows, but there's only one row, so the row space is only a line. I guess it's probably that line. So the row space of B of my matrix is all multiples of 1 minus 1. So it's a line. Let's put the 0 point in. Okay. Then the matrix also has a null space. The null space is the set of solutions to Bx equals 0. It's a line. In fact, it's a perpendicular line. So this is the null space of B, and it contains all, what does it contain? All the solutions to Bu equals 0, which in this case are all multiples of 1, 1. And just to come back to my early comment, that's what the QR, the sort of extra half of the QR algorithm is telling us. It's giving us a beautiful basis for the null space. And so the key point is that the null space is always perpendicular to the row space, which of course we see here. This Z is what we had to compute when there was when there were P components and not just one. And now where is let's see, what else goes into this picture? Where are the solutions to my equation Bu equal D? So my equation was U1 minus U2 equal a particular number 6. And where are the solutions to U1 minus U2 equals 6? Okay, so now I want to draw let me draw, where are all the, so this is the U1, U2 plane. Okay, so one solution is take C equal to 3. 3 minus 3, the combination 3 minus 3, which is right there, is my particular solution. U particular, or U row space, is 3 minus 3. That solves the equation, and it lies in the row space. And now, if you understand the whole point of linear equations, where are the rest of the solutions? How do I draw the rest of the solutions? Well, to a particular solution, I add on any null space solution. The null space solutions go this way. So I add on, so this is my whole line of all solutions. So this is the line of all solutions. And now the key question is, which solution is the smallest? So this is the idea of the pseudo-inverse. When there are many solutions, pick the smallest one. Pick the shortest one. It's the most stable somehow. It's the natural one. And which one is it? Okay, so here's the origin. What point on that line is closest to the origin? What point minimizes u1 squared plus u2 squared? Everybody can see this guy. So the pseudo-inverse says, wait a minute, when you've got a whole line of solutions, just tell me a good one. Tell me the special one. And the special one is the one in the row space. And that's the one that the pseudo-inverse picks. So the pseudo-inverse of a matrix, so the general rule is, and so part of the lecture was the fact that as alpha goes to infinity in this problem, the pseudo-inverse will do it. Or I could say just directly, what does the pseudo-inverse do? The pseudo-inverse, so B plus, the pseudo-inverse, chooses, it chooses UP, if you like. UP. That's the B plus that multiplies the solution. I can't say B inverse D. I mean, everybody knows my equation is BU equal D. So this is my equation, BU equal D. And my particular solution, my pseudo solution, my best solution is going to be B plus D, and it's going to be in the row space. And because it's the smallest solution. So if you meet the idea of pseudo-inverses, now you know what it's talking about. We've got, because we don't have a true inverse, we have a whole line of solutions. We want to pick one, and the pseudo-inverse picks this one. It's the one in the row space, and it's the shortest. Because these are orthogonal, see, because these are orthogonal, the U is UP plus UN. And because those are orthogonal, the length of U squared by Pythagoras is the length of UP squared plus the length of UN squared. And which one is shortest? The one that has no UN. That orthogonal component might as well be 0 if you want the shortest. So all solutions have this, and this is the length of the shortest one. Okay, so that tells you what the pseudo-inverse is, and at least it tells you what it is for a 1×2 matrix. I could, let me, as long as I'm speaking about the pseudo-inverse, let me complete this thought. But you saw the idea of the thought was, there are two ways to get it again. The null space method that goes for it directly, or the big alpha method that we checked actually works. So that was the point of this board here, that the big alpha method also produces, in the limit, as alpha goes to infinity, UP. And there's some little, it doesn't have, if alpha was 1,000, I wouldn't get exactly the right answer, because this would be 2001 in the denominator. But as 1,000 becomes 1,000,000 and alpha goes to infinity, I get the exact one. Okay. So, here I was going to draw the picture. So if I draw a row space, can I imagine this is a row space? whose dimension is the rank of the matrix. Perpendicular to it is a null space whose dimension is the rest, the rank, that was the rank that I'll always call R. Then this will have the dimension n minus R, the number of, this is exactly, these are the two things that that MATLAB found here. These were the R vectors in the row space, turned into columns. And these were the n minus R, but that was only one, vectors in the null space. So normally, we're up in n dimensions, not just two. With 2 dimensions, I just had lines. In n dimensions, I have an R dimensional subspace perpendicular to an n minus R dimensional subspace. And now B, what does B do? Okay, so suppose I take a vector un in the null space of B. Then B takes it to 0. So can I just draw that with an arrow? This will be 0. BUN is 0. That's the whole idea. Okay. But a vector in the row space is not taken to 0. B will take that into the, let's see, I better draw here, the column space of B. Okay, which I'm drawing as a subspace whose dimension is also is the same rank R. That's the great fact about matrices, that the number of independent rows equals the number of independent columns. So this guy heads off to some BU row space, okay? And if I complete the picture, as I really should, there's another subspace over here which happened to be the 0 subspace in this example, but usually it's here. It's the null space of B transpose. In that example, B transpose was 1 minus 1, and that was, its column was independent, so there was no null space. So I had a simple picture, and that's why I wanted to draw you a bigger picture with its dimension will be, well, not n minus R, but if B is m by n, let's say, then it turns out that this null space will have dimension m minus R. No problem. Okay, now, in the last 3 minutes, I want to draw the pseudo-inverse. So what I'm saying is that every matrix B, every rectangular or square matrix B, has these 4 spaces, 4 fundamental subspaces they've come to be called. Okay. And the null space is the vectors which B takes to 0. B takes any vector into its column space. So now let me just draw what happens to U equal U null space plus U row space. So this was a guy in the row space. If B, what will B do when it multiplies this vector? This vector has a part that's in the null space and a part that's in the row space. But when I multiply by B, what happens to this part? Gone. When I multiply that by B, where does it go? There. So all these guys feed into that same point. BU is also going there. That's why it's not invertible. Of course. That's why it's not invertible. Here, I guess, here I'm. So this, sorry, wait a minute. Yeah. this was the null space of B. I didn't write in what was the null space of. Okay. So the matrix couldn't be invertible. And actually, because it has a null space, and they all send those. So what is the pseudo-inverse, finally? Finally, last moment. The pseudo-inverse is the matrix. It's like an inverse matrix that comes backwards, right? It reverses what B does. What it cannot do is reverse stuff that's appeared at 0. No matrix could send 0 back to UN, right? If I multiply by the 0 vector, I'm only going to get the 0 vector. So the pseudo-inverse has to, what it can do is it can send this stuff back to this. This is what the pseudo-inverse does. If I had a different colored chalk, I would use it now. But let me use 2 arrows, or even 3. This is what the pseudo-inverse does. It takes the column space and sends it back to the row space. And because these have the same dimension R, the point is inside B is this R by R matrix that's cool. It's totally invertible. And B plus inverts it. So from row space to column space goes B. From column space back to row space comes the pseudo-inverse. But I can't call it a genuine inverse because all this stuff, including 0, the best I can do is send those all back to 0. There, now I've really wiped out that figure, but I'll put the 3 arrows there that make it crystal clear. So those 3 arrows are indicating what the pseudo-inverse does. It takes the column space, its column space is the row space. The column space of B plus is the row space of B. You know, sort of in these two spaces, that's where the pseudo-inverse is alive. And B kills the null space, and B plus kills the null space, the other null space, the null space of B transpose. Anyway, that pseudo-inverse is at the center of the whole theory here. If when I take out books from the library about regularizing least squares, they begin by explaining the pseudo-inverse, which, as we've seen, arises as alpha goes to infinity or 0, whichever end we're at. And what I have still to do next time is what happens if I'm not prepared to go all the way to the pseudo-inverse because it blows up on me, and I want a finite alpha. What should that alpha be? And that alpha will be determined by, as I said, somehow by the noise level in the system, right? And just to emphasize another example that I'll probably mention, CT scans, MRI, all those things that are trying to reconstruct results from a limited number of measurements that are not really enough to perfect reconstruction. So this is the theory of imperfect reconstruction, if I can invent an expression. Having met perfect reconstruction in the world of wavelets and signal processing, this is the subject of imperfect reconstruction, and I'll hope to do justice to it on Wednesday. Okay, thank you.